We continue with part C of our course. In this part on capacity demand type problems in reliability, we have so far looked at FORM, the first order reliability method, the SORM, the second order reliability method, and in the previous lecture we looked at Monte Carlo simulations for component reliability problems. Today we are going to look at importance sampling as one of the variance reduction techniques in Monte Carlo simulations. Now, why would we be interested in something like this? Let's recall what we learned yesterday. We perform Monte Carlo simulations repeatedly to estimate an unknown probability, typically a very small probability, by generating IID samples from the joint distribution of the basic variables of the problem, and the estimate p hat, which is in some sense an average of an indicator function, is a random quantity because of the finite sample size. So this estimate p hat has a mean of p itself, so it's unbiased, its mean is the true value. Its variance, the variance of p hat, goes down with 1 over n, provided the samples are IID, which actually points to an inefficient convergence. It's the COV, the coefficient of variation of the estimate, goes down with 1 over square root of n. So the question naturally is that can we do better? Here is an example that we saw. If we want to limit the COV to 10%, our number of samples that we would need to generate would be of the order of 100 over p. So just as an example, if p is say 1 in a million, which is very small, but suppose it was, we would need to generate about 100 million samples or run 100 million trials, which could be very demanding if every trial required a detailed and involved finite element analysis of the structure. So whether it's 1 in a million or 1 in 100,000, you get the idea. So let's look at this issue of inefficient convergence and what might be done about it in a graphical manner. So let's see if I can run this movie. This is a bivariate problem. We have capacity C and D, and the limit state is a straight line between C and D. It's C equals D, and we will generate just 1,000 samples and estimate PF. So what you see are the concentric circles on the plane, which indicate the PDF, the joint PDF contours of C and D, and the third dimension is the probability density. So clearly, and as is quite usual, most of the probability mass is concentrated well into the safe area. So it's quite obvious that we are going to get a point generated on the plane quite rarely in the failure region, and that's exactly what happens as we see in this movie. So we have started generating points, and you can clearly see that most of these points have fallen in the safe region, and it appears something like about 11 points out of 1,000 fell in the failed region. Let's run the program again. Let's run the movie again and see what we are getting. So this time I'm going to pause it just before the end. So it's something like 11 in 1,000. So one might wonder that so many points that fell in the safe region are in some sense wasted. We find use only for those 11 points or so that gave rise to failure. So can we not do something? Can we either make use of those points that fell in the safe region, or alternatively, can we generate more points in the failure region? Now, obviously, that is not the true situation, but perhaps we could correct for that bias. And let's see what would happen if we did something like that. So here we have this more efficient sampling sort of scheme. Let's run the movie. We're going to just generate 100 points, and let us see what comes out of that. So the first thing you'll see that we are moving the density function closer to the limit state, closer to the failure region. So let's see if the movie works. Yes. So we move the density function closer to the limit state, and now obviously many more points have fallen in the failure region, and then it seems that our estimated reliability is still about 1.15%, which agrees quite well with the basic Monte Carlo scheme that we used in the previous slide. There also we had about 11 in 1,000, about 1.1%. Let's run this movie again just to see what's happening, and then we will continue with the formal presentation of this method.